So, welcome to 6035. This last sheet I gave at the end of the class, the last part I'm going to do in the class is look at what compile optimizers do. So, just to do that, I thought it would be fun for you guys to actually see whether you have, if you have just a few minutes, just look at this. And I will see whether, if I have time, I will give you 2 or 3 minutes before I get into that section. So you can actually see whether you can beat me in optimizing the program. So we'll see. But I thought you can do something better than me. So, okay, so hopefully everybody had a good summer and ready to get going. And so what we are going to do today is spend some time on course administration stuff. Because this is a large project course, a lot of things starting from today basically get going, and so everybody has to be right on top of what's going on. And then latter half of the course I will just introduce what this class is all about, why you should be here, and why it's interesting to learn this material, and just go a little bit into the flow of how a compiler is built. So for administration, so let me just jump into this. So I am Saman, and I sit in this building up there in 7th floor. My main interests are in compilers, and I am very interested in a lot of low-level compiler and computer architecture where it meets. And a lot of times, traditionally, compilers means try to run things faster. But there are a lot of interesting things on how compiler type technology can help in security and many other domains it's applying. So I'm interested in a lot of those areas. So this is a passion for me. So it's my bread and butter. You guys are I'm going to talk to you guys about, and I'm going to co-teach this class with Martin. And do you answer a little bit what you work on?
Sure. So I tend to work on. So Saman tends to be very close to the hardware. It works on the part of the compiler that maps the program down to the hardware for efficiency. I tend to work at a higher level in the stack where I'm more interested in analyzing what the program does and with a view towards program optimization and also towards understanding whether the program is correct or not. More recently, I've become interested in understanding how, what ways of leaving the bug in the program and letting it continue to execute to see if it gives you an acceptable result, rather than focusing on how to correct the program to get all the bugs out. So I think Saman and I kind of split the area of traditional compilation between us. He focuses more on the low end where you have the computation down on the hardware. I focus more on the high end where you analyze the program and find some information out about it.
Okay, so there's Mary sitting in the back, and she's the most important person for you to know about. She has all the administrative stuff. Her office will have previous course notes and stuff like that. So and Punya is going to be your TA. And so if you have a lot of problems, any problem with the project or stuff like that, he's the person to run to. So we don't have a textbook in this class. So we don't recommend anybody going and spending money buying these textbooks. But if you are really interested in compilers, and if you really think this is an interesting area, if you want to get more information, so there are these 3 textbooks, the Tiger book, the Whale book, and the Dragon book. Can you guys see this? Okay. It's hard for me to even see from here. Just check it out from the library if you need, and I think the reading room might have it upstairs in the 8th floor. But unless you are really thinking that you want to do this for your career, I don't recommend buying these books. So this course is all about a big project. So at the end of the day, all of you guys will build a substantial compiler. And that's a huge project, a lot of cool stuff going on around the project. So because of that, the class basically structured around the project. So the project has 5 segments. So there's a lexical and syntax analysis part. That's where I'm going to basically get started from tomorrow. There's a semantic analysis. So we just basically, I will go describe what these things are in a little while. And then we generate code. So in the midterm, we actually have an end-to-end compiler. So write a program, get it working on a machine. So it's cool. In the middle of the term, we get that. And then we start doing some interesting optimizations, start segment that do data flow optimizations and do instruction optimization. So after that, you actually have a program not only running, actually running faster. So the way we do it is we start a segment. So for example, the first segment starts tomorrow. There will be a project description, and Punya will have a session explaining to you what the project is about, all those things you need to know about the project. Then we have 2 or 4 lectures immediately describing the theory around that area and all the interesting high-level stuff that you need to know to do this part of the project. And then you have a project time. You just go, and sometimes it could be a week, 2 weeks. If you actually look at this handout, the color-coded handout, there are colors for each project segment. So as you see, tomorrow the first project starts, and after 4 lectures, then you have a few days, and for other projects you have a lot more days actually to work on the project. And then we have this interesting thing called project checkpoint. It's nothing but an insurance policy for you guys. So what project checkpoint, they do it in the middle of the large projects. You just create a tarball of all the things you have been working on and just submit it. And we are going to keep those files. We are never going to look at it until at the end of the submission. At the end of the day, when you submit the project, if everything works and no problem, you pass all the tests and stuff like that, that doesn't matter. You get a good grade, you're happy, and everybody's happy. But assume that at the end of the day, your project really didn't work. It's not passing the test, there are bugs in it, and you have a lot of issues in there. At that point, tarball become very important, that tarball, the checkpoint, because traditionally, a lot of MIT students start doing this project about 24 hours before it's due. And the interesting thing about a project like this is you cannot really get it done. You really need to put a few weeks of work. The reason we have given 2 weeks is needed 2 weeks. So what tarball says is that it's a checkpoint to see how much work you have done at that point. So if the program doesn't work, we will look at the checkpoint code. And if you realize you have actually done a substantial amount of work at that point, and you have been working continuously and still you didn't manage to get it done, we'll be very lenient in grading. We'll say, okay, look, you work hard, and every time these things are very complex things and things go wrong. That's okay. But on the other hand, if you look at the tarball and it's basically nothing but an empty file, okay, then that means you started the day before and didn't work. I mean, there's no excuse for that. And then we'll be very harsh in grading. So in that sense, it's a pure insurance policy. So the key thing is get done before, at least think about as 2 deadlines. So instead of saying the project is due, at least there are 2 deadlines. So if your normal thing is to work for 3 days before the deadline, at least you'll have 6 days. So we'll see. And finally the project is due, and then we move to the next section. So that's the way the class is going to work. So the projects are done in groups. Here's a project that I don't think, if any of you, how good a programmer you are, if you say I'm going to do it myself, it's not doable because there's so much work to be done in this type of project. So what that means is we are going to today and until I think we have a piece of paper to submit possible groups. If you know you're already a group, if you already have 3 or 4 people together, just fill it out. Otherwise, Punya is going to collect these things and try to form groups and get it done as soon as possible. And hopefully by the weekend, we will actually have groups. We do not want anybody more than, we like to have groups of 3. Groups of 2 doesn't really work. So we'll really actually, 3 and 4 is basically, we don't want bigger groups either. So sometimes people say, I have 2 people, I won't do a 2-person group. And then what happens is somebody drops out in the middle, and then things get really ugly. And so what that means is grading is, large part of the grade is given for the project. So it's basically the entire group mainly symposium together. So here's one thing I used to tell students in this class. For a lot of people, so taking this class over the years, many people did really well, got A's. Few people who really didn't do well, if for example there have been a few people who actually passed this class, they didn't pass this class not because they were bad coders. That's because they never managed to get a group project going. I can remember there was one group where 2 guys had a disagreement on how IR should be designed, and they start submitting different IRs on CVS in competition, and at some point they start creating a script that automatically keeps submitting. So they spend 2 days just basically submitting 2 IRs and creating a very large CVS log, but never making any progress. Okay, that entire group basically failed the course because they never managed to get anything working because they were all arguing and never getting there. I mean, that's the key thing is if you have a good group going together, divide the task, you won't have that much problem. But I think the key thing is that, I mean, nobody failed this course because it was too hard or they couldn't get everything done. The 2 or 3 groups that didn't pass that course, that happened because they didn't have group dynamics. So one thing you would probably learn out of this group, this class is, okay, how in a group work together. I mean, this is what you guys are going to do. If you leave, I mean, you're not going to sit in somewhere and just do things by yourself. You'll be working in groups. How you get a group project going, how do you get a task divided, and get something done in a very tight schedule. I think that's a very interesting learning project that you'll get out of this course. And the people who manage that well do really well in this class. Don't get stressed out because the class can get things done. So to help the project, you are going to each group is going to have a weekly meeting with the TA. Punya will arrange when the weekly meeting is going to be. It's time to basically ask questions, because one thing we do in this class is we give you huge amount of freedom to design the compiler. This is actually in some sense a great thing and some sense a scary thing. It's scary because a lot of times early decisions you do in the compiler can have drastic consequences later. Because you don't know what coming out in optimizations. You think this is the right thing to do now. But when you could optimize, you realize, wait a minute, that decision was really bad. Because it means that the optimization doesn't work that well. You have to rewrite large chunks and stuff like that happens. So that's why having somebody like Punya to talk and say what your design decisions are is very important. He can point out saying, look, if you do this, if you don't create basic blocks now, what's going to happen is if you start doing data flow optimizations in a month, you will run into problems. So things like that is very important. So even though you think you have a good design, just go talk to him, because for the current project it will work, but there might be consequences happening later. And there's no room to say like, okay, I'm going to redo, because everything just builds on your previous part. So if things doesn't work now or things doesn't work that well, it's very hard to keep building on top of that. So make sure that you really use him as a resource, really brainstorm what you're doing. And the other thing that's going to happen in those meetings is he get a chance to figure out who's contributing to the project. So when you have 3-person project, sometimes if one person is taking 80% of the load, that's not fair. And he'll get a really good view of what everybody is doing, and that will reflect on your grade. So if you just don't show up to his meeting, that he's going to assume that you're not actually participating in the project. So show up to his meetings, have these discussions. So before you implement, at least talk to him about what you're doing and get some feedback. And that's very important. Because a lot of times what happens for people is, especially when they went to optimizations, they find some early decisions are really hurting them. Because they figured out this is easy way to do it, did something, it worked then, but then when you go to do the next thing, they realize, wait a minute, now I have created this entire huge structure around this one concept that doesn't really match. So, as you expect, this is a class that's a huge project. So most of the grade is based on the project. We are doing this interesting thing called paper discussion that I will get to in a few seconds. And then we are going to have 3 quizzes. And that constitutes your grade. And the project is also, the biggest part is the code generation part, and then we have 2 optimization parts coming on. So this is how we are going to divide the grade. So, and then we are going to have 3 in-class quizzes. So 50 minutes long, open book, open notes. Only thing I would say is come on time. So paper discussions. So what's this all about? So you guys come to this class, sit there, sit in the back, and listen to me and go. I never get a chance to talk to people individually. This is a chance for me to interact with everybody individually. So what we decided was, we will 3 times in the semester, we will give a paper out, research paper. Okay? And you guys read the paper and try to understand what the paper is doing and start thinking like a researcher. So if I'm reading a paper, what would I do? I mean, I'm not just reading most of the time to gain information. I am thinking about paper as a researcher. Is this paper, what do they do for research, how important it is, how does it fit in there, do you really believe what they are saying, that do you find problems with it, and there are a lot of interesting research type issues in there. So you guys think about that, write a very small summary, and come and spend 15 to 20 minutes, we haven't figured out how much depending on the size of the class and stuff like that, one-on-one with either me, Martin or Punya, 3 times basically, so you'll get one with each, and then we'll have a small discussion, okay? And what I'm looking is if you find something really cool about it, interesting angle, that it's not just to come and tell me the summary, okay, here's what happened in the paper. I don't want a summary, I can do that, but I want to figure out, can you guys go beyond the summary and then come up with something interesting? So I think this interesting time, I think I don't want to make it, so the reason we actually assign a grade is I want people to take it seriously, but I don't want people to stress out on because of that. So this is a kind of experiment I want to do and see what happens. So I want it to be a fun, interesting, creative thing to do than a very high stress thing or something you don't care. But because I want everybody to participate in it. So let's see. So what we'll do is we will give us 3 interesting papers. You will see, you can read and get a feel for going from a very structured class type thing. If you start doing research, what do you do? How do you understand what other people are doing? Okay, good. So that's basically describes the course administration. Any questions? Quiet. Okay, so the other thing is, since the class is not that big, if people have questions, just don't hesitate to ask. Hey, you can be on TV if you ask questions. But if you don't want to be in TV, though, that's okay too. Still keep asking questions because it's fun. Otherwise, it's really boring for me to come and just say what I say and have a bunch of blank faces in the other end. It doesn't help. So okay. So let's go a little bit into the course material. What are compilers? Why should any of you learn about it? And then go a little bit deep into how do you build a compiler and what's in a compiler. So what do you have to do? We basically, the main thing about that is I have to instruct computers to do things. Computers basically are everywhere, but somebody has to tell them to carry out its instruction. So last 20 minutes I spent telling you guys to carry out the instructions for the course. So I knew how to instruct you. I just come here and speak and say, you do this, you do the project, this is what you have to do. But how do I do it with the computer? And also, it's not just telling that is not enough. How do I get the computer to do it efficiently? I know when I ask you guys to go do a project, you know how to exactly get it efficiently down, do it very fast, whatever, and I think MIT students have that down really nicely. But computers don't come with that intelligence, and it's part of what I have to do is actually get the computer to do what I want it to do in an efficient manner. So the way to do that, if you want the most powerful way to do that, is using a language. The languages use a language to describe what to do is very powerful because using a language, you can describe many things. It's not tied to a context. It's not some kind of a set of pull-down menus that you can select few things and press a button and go do. It's not tied to one thing. You can actually express a lot of general things in using a language. And you can describe the same thing in many ways. It doesn't have very tight structure that really gears you down very specific paths. Most of the languages out there, when I talk about programming languages or even natural languages, it's very flexible. It gives you a lot of opportunity, creativity, and expressiveness of you doing that. Oops, what happened? Just a second. So, how about using a natural language? So, I am spending, and I spend the first part of the time telling you guys what to do in this class using English. So why can't we use English to describe what to do? Well, at least in science fiction, people had tried to use natural language to tell computers what to do. And I guess you know what happened at that point, that it really didn't work out because, at least in that part. So I think the key thing is we are not really there yet. We cannot actually talk to a computer and say what to do. We are beyond science fiction these days. And there are some reasons for that. I think one of the main reasons is natural languages are very ambiguous. Okay, I spend first 20 minutes telling you what this course is about, and I have very literal descriptions. But since I used English, I think there will be few people who find a literal interpretation that completely different from what I thought I told you guys to do. And I always have says, wait a minute, did you say the exam happens this way? I thought it was happening the day after, whatever. And people get confused. And we as humans are very adept to dealing with those kind of confusions and trying to extract meaning out of things. But computers are not good. We are not there yet in computers. They have to be a lot more extract. So that's what programming languages come about. I mean, what we are doing is we are trying to do very explicit and precise way of describing what we want out of the computers. So programming languages basically in high level have to have a bunch of interesting properties. First of all, it has to be precise. So when you describe something, there shouldn't be any ambiguity of how to base what you're describing. So that's a very important thing. It also has nice to be concise. So you don't want to write pages and pages to get something then in a concise way to describe that. It needs to be very expressive, because if you only can do few things and everything you want to do, if you can't describe, it's not a great language. So the language should be expressive. You should be able to build on and do a lot of cool things in there. And also the other thing that I think really important is you need to have a lot of high-level abstractions, because what we are doing in compilers is basically building abstractions starting from transistors sitting on a processor, and the processor provides you with a very simple instruction set to basically, you don't want to go muck with that, try to write to a large database or web server. At that level, we are trying to build enough abstraction that you can start thinking at very high level and get this whole thing done at the level that you want to solve, not the level that machines can handle. So to give an interesting example, so if you have a bunch of foot soldiers sitting out there, I assume those are the transistors inside there. So there will be somebody instructing these people to exactly do one thing, like a sergeant just giving instructions. So, but if you think about that, that's almost like assembly language, just telling exactly some very, very low level thing to do. But if you want to run something large like a war by doing everything from top, it doesn't work. So you need to have abstraction layers. So there will be somebody like general who will basically come up with there. It's probably the compiler will take some very high level information and basically try to map it to the next level, trying to figure out, okay, now how do I move the next level and abstraction in there. And then on top of that, there's somebody like you sitting in there basically trying to figure out what's the big picture and what you want to get solved, and then you instruct the next group to go and do that. So that's basically the abstraction layer, and what we are trying to do is basically build things that each layer can handle and move it down. So how do I instruct a computer? So the thing is, in one end, you have this very high-level description you are doing, high-level languages that describes your problem in a very algorithmic way, something like algorithms class you use. It's not that different from there when you describe in high-level language. But on the other end, you have a machine. It's just used to dealing with very simple instruction, add something, move value from one register to another, move something to memory. Very low level, very specific, very simple primitives. So the key thing is we need to bridge this gap. We need the compiler basically take this very high level description and try to figure out how to get the basic resources to carry out what you want to do and do it right. So this is basically what we have to do that. So we have a high-level program written in a programming language. And then at the end of the day, when you are done, we are outputting some low-level assembly instructions. Okay, that's what you have to do. So how do you do that? So first of all, this programming language is written in the text somewhere in this language. You have to read and understand the program. So you have to say, okay, what's that say? I mean, you need to get that information in there, figure out what that information means, and then precisely determine what actions that need to carry out to execute that set of that program. And then there are a lot of choices. I mean, the thing about that is when you look at a program, it doesn't tell you where to put values, what registers to use, what memory to use, nothing. It just gives a very high level description in there. And then you have a lot of these choices and figure out what's the best choice to do these things. And then basically generate correct, precise code to basically carry out it in your CPU. So here's the first thing. So you write a program like that, a few lines of code, and what come out at the end of the day is a piece of assembly code. That's a lot more low level, divided into much more small pieces. So this is basically, we start high level and you end up here at the end of the course. So at actually mid level of the code. So the other thing is, when you do that, you have many different ways of doing things. So for example, you can have high level thing, and if you have variable, you can put the variable in a register, you can put it in memory, you might be able to not put it in anywhere and carry out directly, eliminate that use of variable. There are a lot of ways of doing things. And it's up to us to figure out what way to do that. And there are consequences. And depending on what we are optimizing or what we are trying to maximize, we make different decisions. So this is basically the second part of the course. So after we generate these things, we figure out, okay, our main focus is going to be run things faster, but what choices you need to make to run things faster. And you can do even more things. We make a lot of these kind of decisions in compile, high level decisions, trying to kind of do what you want to do in principle, but I have a lot of freedom to do that. So I think what you find is, if you just do the simplest thing, the programs will run pretty slowly. And so what that's going to do is, you can build a compiler that carries out your instructions, but if it becomes too inefficient, nobody's going to use those languages. So what happens was, things like high level languages took time to mature and people to use, because at the beginning they have interesting problems. You have very interesting problems. You want to get those things done, and if you express in high level language, and then you can't get it done on time, if it doesn't feature on the memory of the machine, you have a lot of problems. It's useless that having a high level language, even though you can nicely write it in there. So you're going to go try to do this in low level. So the thing about the compile is, what it has to do is, it has to basically having this inefficient abstraction is useless. So what it has to do is provide this abstraction, but get it working like you actually did it in assembly level. So the nice thing is, you write it in high level abstraction, and all the results you get because of the compiler looks like you actually managed to do it in assembly level, and it gives you that freedom. So that gives you nice freedom. This is very important. Like for example, when Java start coming, there are a lot of people who start doing real-time type applications. There are companies who try to do graphics editors in Java and gave up because things were too slow. And it took some time for the language to get to a point that you can actually go do more real-time things. The compilers have to evolve. And still there are some stuff that people, like very low-level code, that people will not write in Java. There are some code people don't even write in C because they can't get the efficiency in there. Well, hopefully the thing is, the compilers can be better and better. So this mapping that you can actually say, I can do this high-level language, and I don't have to care about the inefficiency, because there won't be that much inefficiency. So how are you doing in time? Okay, I think I'm doing good in time. So what I'm going to do is start all of us into a path to think like a compiler. So here's an example program. Just I wrote some night. Just it doesn't mean anything, but it has a lot of inefficiencies. A lot of code we write has these kind of inefficiencies. Now I want to go and figure out how well I can actually map that. So I actually gave you a piece of paper in there. I'm not going to collect that. Why don't I give you we'll say about 4 minutes to see whether you can look at that and see how you can eliminate and do it very efficiently. You can talk to your neighbors and stuff like that. This is not a test. But at the end of the day, I will basically walk you through a bunch of steps that normally a compiler carries, and then we can see how well you can match that. wireless.
Yeah, I'm just working on some presentation.
Okay. Is the normal size of? So it's just a fun exercise. It's not a test. So let's actually go try to see what a compiler will do here. So here is if you do just unoptimized code generation. So you don't do anything. You just go and say, I just want to run this without changing anything, and this is what will happen. So just you don't have to understand this. This just out there. I'm going to put these slides on the network, so you'll know what's going on. So let's go and optimize. So what's the first thing? First thing is what we call constant propagation. So the constant propagation says there are a lot of times things are constant. If you know a variable is a constant within a range, that means every time I go execute that range, it has the same value. I don't have to actually I can basically propagate that value down directly. So what are the constants here? So the first thing is this a constant? X equals 0. Can I propagate that? Not really, because what happens is oops. What happened? Did I go down? Sorry, let me go. Okay, so here we go. So because of the x is getting modified in here, so x is not a constant, so every iteration you get a different value for x, so I can't propagate x in here. But on the other hand, if I go look at y is basically assigned to 0, and it never changes within this loop in here. So I can easily go and say, okay, I'm going to replace that y by 0. I actually don't have to do that calculation. I get a lot of interesting savings in there. Next thing I can do is algebraic simplification. A lot of times humans, it's nice to write these nice descriptive expressions, but there are a lot of simplifications you can do that. What can we do here? So for example, now after constant propagation, we are actually multiplying b by 0. Why waste time? You know it's 0, and you can just do 0. And the next thing we can do is, okay, now we are adding 0 to x. Why just do that? We can just go and eliminate that and just make it x. So another interesting principle in compilers is we do things in very small granularities. We are not trying to do this. I mean, as humans, we look at many things and just in one go do a very large change to things. In a compiler, it's very hard to do that. What we do is we do just micro changes. In here also, what you see is I didn't try to do saying, okay, I am multiplying by 0 and then adding, and therefore I can eliminate everything. I just go with this baby steps. I said, wait. I will do a very simple step, which is this first multiplication by 0. I eliminate that, and I will put 0 in there. It might not be used, but the next time round I will get those things. So I'd rather do things, very simple things, many times, because compilers are run by a computer. It can do, the nice thing about computers is they can do many things. So you want to do simple things many times than complex things few times. So a lot of times when you're developing compile algorithms, we try to figure out some very simple things you can do. That alone might not be that important, but doing that with others and doing it many times actually can make the program much better. So okay, now we are in here. We are assigning x to x. That sounds like a boring, stupid thing to do. If you are human, you will never get there. But as a compiler, you want this as intermediate step. And then we do copy propagation, which basically says if you are assigning the same thing, why do that? I mean, you can use the other variable in there. And so I can just basically eliminate that in there. And what else can we do? Another interesting thing we will do in compilers is common subexpression elimination. That means I am calculating the same thing twice. Okay. If I'm calculating the same thing twice, why do that? I'll calculate it once and use it twice. So here, I realize I am doing I plus 1 twice. So instead of doing that, I can just basically create a temporary variable and do the calculate that and replace that. So note that even though I'm saying that as this is always obvious win-win situations, something happened here. I actually had extra storage. So now instead of doing just I plus 1, I actually have this intermediate t value that I'm calculating, I'm putting in there, and I'm storing it. So the compilers get very complex because at some point you might want to get speed, but you're running out of space. You don't have that many registers, and things like that. A lot of this, the complexity comes about by doing things that are not always the right thing to do. So at this one, I'm assuming that, okay, I'm just going after making it run faster. So I just add a variable and got rid of that 2 additions and a multiply, just down to 1 addition and 1 multiply. So what else can we do? Dead code elimination. So a lot of times humans by mistake, when you're writing the program, do some calculations and that never get used. Most probably after some of these transformations, we have eliminated the use of very things in there. So for example, in here, this y equals 0, we are never using y. Because we eliminated, we suddenly realized constant propagation can eliminate the use of y, and suddenly we have this expression sitting out there. I'm calculating a value I'm never using. So why? I can just get rid of that one and eliminate both storage and a computation. It's getting nicer and nicer. What else can we do? So another thing is loop invariant removal. So what that means is in a loop, you are going round and round many times. And if you are doing something, same computation again and again and again and again, you can do it once outside the loop, use the value inside the loop. So here we have expression in here that never changes. It's the same value every time you go through the loop. So why don't I just calculate it once out there and use it? And things get simple. So inside the loop, instead of doing a multiplication and division and 2 multiplication and division, I just end up doing 1 multiplication there for that sub expression. So okay, so now we are getting smaller and smaller. What's next? So here's an interesting one. For most processors, addition is cheaper than multiplication, because a lot of processors have more adders, and adders are cheaper because you can actually pipeline them and do it much faster. Multiplication takes a lot longer. So there are a lot of transformations trying to convert one type of operations to cheaper operation. So that's called strength reduction. So the strength reduction transformation here is I took this multiplication and realized that I is a loop invariant. So every iteration, The first iteration, I multiplied by 0 is, u multiplied by 0 is 0, then u, 2u, 3u, 4u. I just keep doing that. And what that means is, I'm basically adding u to this computation every time I go there. That basically become adding 1 u. So why don't I change that to basically addition? This is also interesting one, because here what I'm doing is I can add a little bit more storage to keep that value, and then I can just change the multiplication to addition. So now what I do is I add a variable there, v, that basically keep that value in there, and then I can replace that with v. So I got rid of multiplication, introduce addition. So sometimes it might not be that important depending on the machine, but some machines this is a very important thing to do. So what else can we do? So another interesting thing, strength reduction, is a lot of times shift operations are a lot cheaper than multiplication. Because shift is just pushing some bits around. So if you're multiplying by a power of 2, you can do a shift and get rid of the multiplication. That's another kind of strength reduction you can do. So other big thing in especially RISC type microprocessors is using registers is very efficient. Because most of the time, you can take a value out of register, do operation, and store in a register. This happens much faster. Using memory is expensive. And a lot of times at the beginning, when you start a program, you put everything in memory, because there's no restrictions in memory. Memory is unlimited as far as you are concerned. So it's very easy to put everything in memory. Either in the stack, if you are a local variable, or heap. If it is global variable, just keep everything in memory. But the consequence is, every time you want to do operation, you have to get it out of the memory, do something, put it back. And so that's a lot more expensive. So one big win in compilers is saying, wait a minute, I have registers. I don't have to always work with memory. I can keep things in registers. Instead of getting into a register, operate, and put it back, why can't I keep a value in register for a long time? So in here, what we can do is, we realize we have this, and the thing about that is, the reason we don't do it just at the beginning is, there are very limited number of registers. You can't just go and say, okay, I put every variable in register, because there are hundreds of variables in programs, but limited registers. And so here what we realize is, wait a minute, I don't have that many variables in this program. I can keep everything in a register. So by doing that, I can actually get rid of a lot of these memory operations. So I can't show this in C program because it doesn't change anything. So at the end of the day, if I do all this optimization, I end up with a program like this. Did anybody do better than me? Did anybody find anything better than me? Okay.
Just out of curiosity, can we get rid of the t equals I plus 1 and instead just add an extra?
Yep, exactly. So that's a very good point. Because I am actually doing t equals I plus 1 and I just keep I. Why do I do that? I can basically just roll it into this computation there. That's good. Good point. Very good point. Because how can you actually do this? This is interesting. What's a good way to eliminate both t and I? What are my choices?
Why don't you use and just count the number of times you do the same time you use I?
Okay, so one way to do that is, one way to get rid of t is basically use the loop index based on t. So instead of going I equals 0 to n, I can go t equals 1 to n plus 1. So at that point, I don't need I anymore because I'm not using I at all. So at that point, I can completely get rid of I. So that's optimization I missed.
I don't think you were saying that. Were you saying that?
I think that's better. What I was saying is change t equals I plus 1 t plus plus, and then set t equals 0 before the loop.
Oh, okay.
And so that it just copies I almost.
Yeah, but still, yeah. But if you do that, still you have to do the addition. I mean, either you t plus I or t plus 1. Right. So I don't think I reduce operation at that point.
Well, I was also thinking that you wouldn't need I anymore to go through the loop. You would just.
So what he's talking about actually has very interesting implications, because a lot of times, if you even go deeper to this, programs are So normal microprocess, I'm just going a little bit deep in. The normal microprocess doesn't mean you finish executing instruction before you start the next one. Things actually get overlapped. Okay, and so what I'm doing here is I can't calculate the t until I have the next I available. So I have waiting. If I have multiple operations, like a superscalar type machine, if I can do multiple operations in parallel, I have to wait until I get I done. What you say is I can do both parallelly, because my t doesn't depend on I, because I calculate t independently. So I can actually get a win there if you do that. But I think here you can even do better. You can just completely get rid of I and base it then and reduce that.
Is any compiler smart enough to recognize what the summation is and just replace it with a static form of the summation?
Some things people do. Lot of times they are not robust, because what that means is, so here's a dirty little secret in compiler world. So a lot of times compilers, they work in getting these benchmarks run faster. So they said, aha, that benchmark has that pattern, and I'm going to look at that pattern. In fact, there was a compiler there was a benchmark that was written by a person named Jack Dongarra. So there was optimization that normally can't be done because it's unsafe, but that program they could do. So what the compiler did was check for the word Jack Dongarra. If Jack Dongarra is present, go do that to that loop, because you knew that that benchmark will work. So people have done things like that. And there are other common patterns, common idioms to look for. But the thing is, for example, look at something like FFT. There are great ways to run FFT very fast. But the problem is, if you try to write a fast Fourier transformation loop in C, 10 people will try it very differently. So how do you figure out, how do you match, pattern match to get that expression is harder. So it's much easier to do some kind of general mathematical reduction or something like that. So you, instead of trying to say, look for FFT, you actually come up with some kind of a mathematical framework to look at that type of a thing, that even if you change a little bit, still you can do some optimization. So people try that, but mostly for specific getting benchmarks faster. So here's the optimized code. The interesting thing is, now if I compare unoptimized to optimized code, so I got before this loop, and I end up producing this loop. And when I really calculate the number of loop iterations, this one, there are 7 instructions you always have to run, and every loop iteration you have to run 21 instructions. If I optimize, I run 9 instructions at the beginning, because I do that. I only have to do 7 instructions in the loop. And at some point of time, I actually wrote this both and did this, and executed on a machine, and this ran 43 seconds, and that ran 17 seconds. So this is the kind of things we can do in a compiler. So I think I have very little time. Let me see, where am I? So, okay, I'm going to, because the other thing is, a lot of times what we are going to focus in this class is performance and speed. We are doing optimization to get code run faster. There are a lot of other things you can do with this information. For example, if you are using a cell phone, it's not performance that matters. It's basically battery life. If a cell phone, the reason you buy one cell phone versus other was you have more battery life. So at that point, the compilation worries about optimizing battery life. Things like code size is important. And for example, the kind of stuff Martin and I are looking at these days is using the analysis information to do things like security of a program. So can we say something about this program? If we run it, it will not leak information. So or it cannot be broken into. Or it can be executed reliably. So there are a lot of other things, because there's a treasure trove of information in that program you write. Okay, just executing that is one thing, but can you mine that and then do other things? There are a lot of interesting things you can do. Okay, so let me stop there. I was going to give a little bit of an introduction of how each part of the compiler sits there, but next lecture Martin is going to probably can start with just giving you a little bit of a flow of the computer. Okay, good. So hopefully we are going to have a fun semester building a compiler.
I'd like to remind everyone that